Ever looked at something like H2O or CO2 and thought, wait, what's that secret chemistry language? Well, that's a chemical formula, chemistry's way of saying what something's made of. It's like the recipe of a substance, showing which atoms are inside and how many of each. Quick, clear, and packed with atomic info in just a few letters and numbers. Let's dive in and decode it. Over to my friend who is going to explain you in detail about what is chemical formula, empirical formula, and molecular formula, and how to decode them. A detailed explanation with examples. So let's start.
First of all, what is meant by chemical formula? Chemical formula is a brief representation of molecules present in an element or compound in terms of symbols of various elements present in it. So if we take an example of water, here you can see the water molecule. Here we are representing different atoms with spheres of different sizes and colors. So this one with the negative sign represents the oxygen atom, and these two represents hydrogen atom. So now if we want to write the formation of water molecules, then how are we going to write this? In terms of this kind of representation, taking the spheres of different sizes and colors, then two atoms of hydrogen you can see here with their green color plus one atom of oxygen of this red color give you one molecule of water, which consists of one atom of oxygen and two atoms of hydrogen. But this kind of representation, that representing different atoms and molecules with sphere of different sizes and color, it's quite complicated and not easily understandable. So this is the reason we are taking into consideration the chemical formula, because the chemical formula is a brief representation of the molecules present in an atom or a compound in terms of symbols of various elements present in it. So if I have to write this in terms of symbols, then how I will write this? It will be H2 plus O gives you H2O, because the symbol of the hydrogen atom is H, whereas that of oxygen is O, and two atoms of hydrogen. This subscript represent the number of atoms of this particular element. So there are two atoms of hydrogen plus one atom of oxygen gives you one molecule of water, which consists of two atoms of hydrogen and one atom of oxygen. So this is quite easy to understand and to write. So this is the reason we are taking into consideration the chemical formula. First of all, it consists of the molecules present in an element or the compound in terms of their symbol, and it is very, very easy to understand. This is the reason we always take into consideration the chemical formula and the chemical equations for understanding the chemical processes and reactions. So now we have understood what is meant by chemical formula. Let us proceed further. Now, chemical formula has been further divided into two forms. One is empirical formula and next is molecular formula. In this video, we'll discuss about empirical formula. Now, what is meant by empirical formula? Empirical formula is the formula of the compound which shows the simplest whole number ratio between the atoms of various elements present in one molecule of a compound. Before understanding this whole concept of empirical formula, first of all, we should understand what is meant by simple whole number ratio. Simple whole number ratio implies that the ratio of atoms of elements in a compound share no common factor. So what does this mean? What is meant by no common factor? This can be understood with the help of an example. Let me take an example of ammonia. Here we have ammonia molecule which consists of one nitrogen atom and three hydrogen atoms. These subscripts represents the ratio of the atoms of elements in a compound. So that means we have one nitrogen atom and three hydrogen atom. We have the ratio of 1:3 in this case. Now, what is meant by no common factor? As you can see here that nothing is common between 1 and 3. There is no common factor which we can use to get the simpler ratio than 1:3 ratio. We cannot get. So that means they don't have any factor in common. And so 1:3 ratio represents the simplest whole number ratio. And please remember one thing, that this ratio will always be positive integers having no common factor. So this formula is the empirical formula of ammonia, because in this the atoms of various elements in one molecule of the compound is present in the simplest whole number ratio. Let us consider a few more examples. First example, sodium sulfate. You can see here this is sodium and we have 2 atoms of sodium. This is sulfur, then we have 1 atom of sulfur. This is oxygen, we have 4 atoms of oxygen. Now let me write the ratio of these elements. This is sodium, then we have sulfur, and then we have oxygen. So this is 2, this is 1, and this is 4. Now you must be thinking that I have told you the concept of no common factor, and here we have a common factor 2 between the sodium atoms and the oxygen atom. So now how I can justify that this is the empirical formula of sodium sulfate? So I would like to tell you here that when I'm taking into consideration the empirical formula, and I'm telling you that the empirical formula of the compound is a formula which shows the simplest whole number ratio, and the simplest whole number ratio represents no common factor. I am taking into consideration that all the atoms of the elements should not have any common factor. Here there is a common factor 2 between 2 and 4, but with sulfur we don't have. So overall, if we consider, we cannot take any common factor among 2, 1 and 4, because 1 will not have any common factor. We cannot take 2 as a common factor here. So in this case, the number of atoms of the sulfur does not bear any common factor with the atoms of the sodium and the oxygen. So we cannot take any common factors. So that means they share no common factor. So this justifies the first condition. The second condition is that these ratios should be positive integers, and they are. So they are positive integers. So these two conditions are justified, so we can consider sodium sulfate, that is 2 atoms of sodium, 1 atom of sulfur, and 4 atoms of oxygen, as the empirical formula of sodium sulfate. Now consider this complex formula. Here, first of all, let me write the ratio of the various elements present. Carbon is to hydrogen is to nitrogen is to oxygen. Carbon has 4 atoms, hydrogen has 8 atoms, nitrogen has 2 atoms, oxygen has 1 atom. So the condition that they bear positive integer is justified. Now the second condition of no common factor, they should not share any common factor. You can see here that there is a common factor among carbon atoms, hydrogen atom and nitrogen atoms. We can always take out 2 as a common factor. But what about the oxygen? Oxygen doesn't have a common factor 2. So in this case also, as oxygen atom does not have a common factor like carbon, hydrogen and nitrogen atoms, so we cannot take any common factor on a whole. So if we take the overall ratio into consideration, we cannot take any common factor. That means the ratio of the atoms of various elements present in this compound have no common factor. So that means we cannot convert this formula into more simpler ratio. So this formula represents the simplest whole number ratio. Thus this represents the empirical formula of this compound. So all you have to remember is just you have to consider 2 conditions, that is no common factor and positive integers. So this one is the most important of one, no common factors. So if there are no common factors, so that means there's atoms of elements bears a simple whole number ratio, and if they bear the simple whole number ratio, that formula represents the empirical formula. First of all, determination by common factor method, the steps. There is just one step. Empirical formula is calculated by dividing the atomicity, that is subscripts, of each element present in a molecule by a whole number, that is a common factor, to give the lowest possible ratio. This is very important. So let us understand this step with help of an example. Here I have taken an example of glucose, that is C6H12O6. This is the actual formula. Let me write the ratios of each element present in glucose. That is carbon atom, hydrogen, and then oxygen. Here we have 6 atoms of carbon, then 12 atoms of oxygen, and then 6 atoms of oxygen here. Now these 3 subscripts are known as atomicity because these represent the number of atoms of each element present. So in the molecule of glucose we have 6 atoms of carbon, we have 12 atoms of hydrogen, we have 6 atoms of oxygen here. Now we have to take their common factor to get the lowest possible ratio. In this case I will take the common factor as 6, so I will divide all of them by 6. So here I will get 1, and here I will get 2, and here I will get 1. So the simplest whole ratio is 1:2:1. That is 1 atom of carbon, 2 atoms of hydrogen, and 1 atom of oxygen. So the empirical formula of glucose will be CH2O because this 1:2:1 represents the simplest whole number ratio. And if you consider the conditions for their empirical formula, that is positive integers and the no common factor, these two are justified by this. This ratio represents positive integer and they have no common factor among them. So CH2O represents the empirical formula of glucose. Now you must be thinking that why I have not taken 2 or 3 as a common factor. So let us consider that case. If I would have taken 2 as a common factor, then the ratio would have come as 3:6:3. Now this ratio will not represent the empirical formula because they still have 3 in common. They represent positive integers, that is fine, but the second condition, that is no common factor, is not justified by this ratio because they have 3 in common. So again we need to divide it by 3 to get 1:2:1. So we would have got the same answer if we would have taken 2 and 3. So instead of doing this longer route, we should choose the common factor accordingly to give the lowest possible ratio. So this is how you determine the empirical formula using this common factor method. Now let us consider a few examples. First, acetylene. Let me write the atoms of different elements present in this compound in the ratio, that is carbon into hydrogen, that is 2:2. So the 2 condition, first the positive integers, they are positive integers, checked. Second is no common factor, but they have common factor as 2. So to express in terms of empirical formula, we have to take out the common factor 2. So we need to divide these 2 atoms by 2 and we will get the answer as 1:1. That is CH1 and 1. This represents the simplest whole number ratio. We cannot have a more simpler ratio than this. So 1:1 represents the simplest whole number ratio. So the formula that we get, that is CH, represents the empirical formula of acetylene. Hydrogen peroxide, that is H2O2. I am writing the ratio of the atoms of the elements present in this formula and this molecule, that is 2:2. Again, these are positive integers, and second, we are taking into consideration the no common factor, but yes, they have a common factor, that is 2. So now to express it in terms of empirical formula, we have to take out the common factor 2. That means we need to divide these atoms by 2 and we will get the ratio as 1:1. So 1:1 represents the simplest whole number ratio that we can get. So the formula that we get, that is H1 and O1, is the empirical formula of hydrogen peroxide. Now let us practice few more. Here we have already done acetylene. We will take the common factor as 2. So the empirical formula will be CH. In ammonia we have 1 atom of nitrogen and we have 3 atoms of hydrogen. There is no common factor, though this ratio represents positive integers, but they don't have any factor in common. So this formula itself represents the empirical formula. So the empirical formula of ammonia will be NH3, same as its actual formula. Next, glucose. As I've told you earlier that we have to take out the common factor to get the least possible ratio. So we need to take out the common factor 6. In this case, the empirical formula will be C1, H2, and O1. Now in case of benzene, you can see here it's C6H6. So we need to take out the common factor 6, and the empirical formula will be C1H1. So if you just see here that none of the ratios have a common factor, so all these represent the empirical formula of these compounds. Percentage composition refers to the percentage by mass of each element present in the compound. What I'm trying to say here, that if we consider this example magnesium carbonate, then what percentage by mass of this element is present in the whole compound? The whole compound is magnesium carbonate. So in this magnesium carbonate, the percentage by mass of magnesium is 28.83%, whereas carbon percentage by mass is 14.24%, whereas the oxygen percentage is the maximum, that is 56.93%. Basically, it is the percentage by mass of each element present in the compound, and we will be using this percentage composition basis to find the empirical formula using this percentage composition method. Let's start with the steps for determination by percentage composition method. Let us consider one example. The example is a compound on analysis was found to contain carbon 48%, hydrogen 2%, whereas oxygen 50%. Calculate its empirical formula. So we will be calculating the empirical formula using the steps. So here are the steps. The first step is to write symbols of all elements. So in this example, we have three compounds, that is carbon, hydrogen, and oxygen, and their symbols are C for carbon, H for hydrogen, and O for oxygen. Now the second step, write percentage composition of each element. As given in the question, that the carbon is present 48%, hydrogen is 2%, whereas oxygen is 50%. Now the next step, write atomic mass of each element. The atomic mass of carbon is 12, the atomic mass of hydrogen is 1, and atomic mass of oxygen is 16. Now the fourth step, calculates moles of each atom, that is divide percentage by atomic mass. So in order to find the moles, we have to divide the percentage of each and every element with its atomic mass. Here are the percentage of carbon, hydrogen, and oxygen as given in the question. So first of all, I'll find the moles of carbon. That will be equal to percentage of the element, that is given as 48, upon its atomic mass, that is 12. So this will come out to be 4. Then moles of hydrogen, that will be the percentage of hydrogen, that is 2, upon atomic mass, that is 1. This will come out to be 2. And then moles of oxygen, so the percentage is given as 50 and the atomic mass is 16, so this will come out to be 3.12. The fifth step, calculate the molar ratio. So to find the molar ratios, we have to divide the moles that we have calculated in step 4 of each element by the lowest mole ratio. So these are the moles that we have calculated. The number of moles of carbon as calculated is 4, whereas the moles of hydrogen is 2, whereas moles of oxygen is 3.12. Now to calculate the molar ratio, we have to divide each of these moles with the lowest mole value. So out of these three, the lowest mole value is of hydrogen. So we will be dividing the moles of these three with this lowest value. So the molar ratio of carbon will be 4 divided by 2. That will come out to be 2. The molar ratio of hydrogen will be 2 divided by 2. That will come out to be 1. And the molar ratio of oxygen, that will come out to be 3.12 divided by 2. So this will come out to be 1.56. Now the sixth step, the last one, calculate the simplest whole number ratio if molar ratio is in decimal or fraction. In the fifth step, we have calculated these molar ratios of carbon, hydrogen, and oxygen. And the molar ratio of oxygen is in decimal. So we cannot write the empirical formula with this. So we need to calculate the simplest whole number ratio. So we have to convert it into an whole number, as these are positive integers. So that justifies the condition for the empirical formula. But this is in decimal or the fraction. So we need to convert it into whole number. So we will be doing it randomly by choosing one number so that it becomes whole. This is roughly 1.5. So if I divide this by 2, this will come out to be a whole number 3. In this case, approximately it will be 3.12, which I can write as 3. So I have converted this decimal into a whole number by multiplying it by 2. So I will do the same with these molar ratio of hydrogen also. This will come out to be 2, and the molar ratio of carbon, this will come out to be 4. So these three represents the simple whole number ratio of carbon, hydrogen, and oxygen. So this is carbon, hydrogen, and oxygen. So these are the simplest whole number ratio. You can very well check that these are positive integers and they don't share any common factor, because 3 doesn't have 2 in common, so they have no common factor. So this justifies the two conditions for the empirical formula. So the empirical formula of this compound will be C4H2O3. This is the answer. So what all steps I have told you in now, I have explained in detail, but while solving the question you have to be quite quick. So this is a shorter method in the form of the table. You first write the elements, then the percentage, and then the atomic mass. Then you calculate the moles, that is dividing the percentage by atomic mass. So here I'm dividing the percentage by atomic mass. Then I will calculate the molar value by dividing these moles by the lowest mole value. So I will get the answer as 2:1 is to 1.56. As 1.56 is a decimal, so we need to convert it into simplest whole number ratio by multiplying it with some number so that we can get the whole value. So here we will get approximately 3, and multiplying with 2 we will get the simplest whole number ratio of hydrogen as 2, whereas that of carbon 4. So I have explained the steps in detail for your understanding, but while solving the question you need to make this table to quickly get the empirical formula. So the empirical formula of this compound is C4H2O3.
Now that you know what chemical, empirical, and molecular formulas are, and how to calculate them, it's time to level up. Check out other videos on our YouTube channel, Trans-E Learning, for practice problems that'll help you master and crack these formulas with confidence. Thank you.